we shall continue our discussion. So the next definition says, so let f from to r a function where d is close to rectangle in R2, that is given by d is equal to set of all ordered pair t such that a is less than or equal to x less than or equal to, and c is less than or equal to t less than or equal to d, the closed rectangle R2. So if limit h tends to 0, f of x plus h comma t minus f of x comma t divided by h exist, then we say that f has a partial derivative at the point x comma t with respect to x, and the limit value is denoted by fx of x comma t, or it's also denoted by dou by dx of f of t. So similarly, if limit k tends to 0, f of x comma t plus k minus f of x comma t divided by k exists, then we say that f has a partial derivative with respect to t, and the limit value is denoted by, it is f suffix t of x comma t, or dou by dou t of f of x comma t. So we shall see the next theorem. Okay, suppose f of comma t and its partial derivatives f t of x comma t are continuous real function on the closed rectangle D, that is nothing but ordered pair x comma t such that less than or equal to x less than or equal to b, c less than or equal to t or equal to d. Define capital F of t is nothing but integration a to b of x comma t dx for each t between c and d, then the theorem says f is differentiable on closed interval c comma d, and f dash of t is equal to integration a to b f suffix t of x comma t dx. So that's the proof. So since given that my partial derivative ft is a real function, it's continuous on the closed rectangle D. On the closed rectangle D, we can say my ft from G to R, that is continuous. Since it is continuous and this D is compact, being a closed rectangle, we can say this ft is uniformly continuous. So given any epsilon greater than 0, there is delta greater than 0, for any comma t, comma z, comma t belongs to D with norm of x comma t minus x dash comma t dash, delta implies we have modulus of f of x t minus ft minus ft of x dash comma t dash is less than epsilon. Now fix t naught belongs to closed interval sigma d, then t belongs to closed interval c comma d with modulus of t minus t naught less than delta. We have as we vary x, that is norm of x comma t minus x comma t naught is less than delta, implies by the uniform continuity of ft, we have ft of x comma t minus ft of x comma t naught is less than epsilon. For any x belongs to closed interval a comma b and t belongs to closed interval c comma b with modulus of t minus t naught less than delta, with t minus t naught less than delta, by mean value theorem we can find s at t, say t1 between, we can find t1 between t and t naught such that f x comma t minus f of x comma t naught is equal to ft of x comma t1 into t minus t naught. Say equation 1. Now for any t with, for any t with 0 less than modulus of t minus t naught less than delta, we have modulus of f of x comma t minus f of x comma t minus f of x comma t naught divided by t minus t naught minus f suffix t of x comma t naught is equal to now using this we have it is equal to f t of x comma 1 minus f t of x t naught. But since t and t naught for any t with 0 less than t comma 0 less than modulus of t minus t naught is less than delta, for this t1 and t naught, difference between t1 and t naught is less than delta, we get this difference is less than epsilon using this. Since modulus of t1 minus t naught is less than delta. So consider modulus of capital F of t minus capital F of t naught divided by t minus t naught minus integration a to b f suffix t of x comma t naught to dx is equal to now it is modulus of, now we know that f of t, capital F of t is nothing but integration a to b f of x comma t dx. So we are taking a common integration for these two terms, that is we have integration a to b, it is f of x comma t, so and this minus, and for this it is integration a to b f of x comma t naught, that is f of x comma t naught whole divided by this t minus t naught minus and this, that is ft of x comma t naught whole into dx. Now using the properties of modulus and integration, wait a second, yeah, this is less than or equal to integration a to b modulus of f of x comma t minus f of x comma t naught divided by t minus t naught minus ft of x comma t naught into dx. Now this is less than epsilon, so it is less than or equal to epsilon into integration a to b dx, and this is nothing but epsilon into d minus a. Since epsilon greater than 3, epsilon greater than 0 is arbitrary, f is differentiable at t naught, so f is differentiable at t naught and what is this derivative? This derivative is nothing but this, that is nothing but f dash of t, nothing in particular t naught is nothing but integration a to b ft of x comma t naught to dx. So since this t naught belongs to c comma d is arbitrary, we have f is differentiable on f is differentiable on closed interval c comma d, and capital F dash of t is nothing but integration a to b ft of x comma t dx. Hence the flow. So continue the next theorem. It's one of the beautiful and interesting theorem. So this theorem is known as interchange theorem. Interchange theorem. So if f is continuous, real function on closed rectangle D, that is nothing but ordered pair x comma t such that a less than or equal to x, less than or equal to b, c less than or equal to t, less than or equal to b. Then integration a to b and integration c to d f of x comma t dt into dx is equal to integration c to d integration a to b f of x comma t dx into dt. So we shall the proof. This theorem says when how this theorem tells how to interchange to integral. So if f is a continuous irregular function on a closed rectangle, then integral can be interchanged. Okay, so we shall observe this proof. So given that f from D to R is continuous, so it is follows that by our previous discussion, function capital F defined by from a closed interval c comma d r by defined by capital F of t is nothing but integration a to b f of x comma t dx is continuous is continuous continuous. This function is continuous. Therefore, we know that continuous continuous functions are Riemann integrable. Therefore, integral c to d capital F of t dt, that is nothing but integral c to d, and f of t is nothing but integration a to b f of x comma t into dt is exists. Similarly, integration a to b integration into d f of x comma t dt into dx is also exist. Now, using the continuity of this f, now f is continuous on this d, and since this d is again observing the similar things, since this d is a closed rectangle, it is compact set, so f is a continuous function on a compact set. Therefore, f is uniformly continuous on d. Therefore, given any epsilon greater than 0, there exists a delta greater than 0 such that for any x comma t comma x dash comma t dash belongs to with norm of x comma t minus dash comma t dash less than delta implies modulus of f of x comma t minus f of x dash comma t dash is less than epsilon. So that is given any epsilon greater than 0, there exists delta greater than 0 such that for any x comma t comma x dash comma t dash belongs to d with, now this is modulus of x minus x dash less than delta and modulus of t minus t dash less than delta implies modulus of f of x comma t minus f of x dash comma t dash is less than epsilon. So let's take this star. Choose a positive integer n sufficiently large such that b minus a by n is less than delta. So choose a positive integer, choose an n belongs to n sufficiently large such that b minus a divided by n is less than delta, and also d minus c divided by n is less than delta. Now choose xj is equal to a plus b minus e divided by n into j, where j varies for all j between 0 less than or equal to j less than or equal to n, and k is nothing but c d minus c divided by n into k where for all k between 0 less than or equal to k less than or equal to n, then the points, so for each j, so we are getting n plus 1 n plus 1 points xj's and tk's. So considering then the points is xj comma tk, where as j varies between n, 0 to n and k varies between 0 to n, then these points divides my our closed rectangle D into n square equal rectangles. So that is, say this is A and this is B, this is C and this is D, then my closed rectangle is nothing but this region. Okay, now xj's are the points. Xj's are the points here, and tk are the points here. So this will divide this rectangle into n square equal smaller rectangles. Well, smaller rectangle. Now integral c to d integral a to b f of x comma t dx into dt is equal to now this is integral c to d. Now integral a to b f of x comma t dx. Now a to b is divided into x naught, x1, so on up to xn. So writing this integral a to b as equal to summation integral x to xi plus 1. In particular, let's say xj minus 1 to xj, that is we get, which is nothing but summation integral xj minus 1 to xj f of x comma t dx into dt, where this summation varies over j is equal to 1 to n. So this is using my property of integral. Again, this is equal to integral c to d summation j equal to 1 to n. Now this is written as f of x j dash comma t into xj minus 1 into dt, since by first mean value theorem, using first mean value theorem, where this xj dash is belongs to the closed interval x minus 1 comma xj for and this xj is some point between, it's some point in between xj minus 1 and xj, and this is true for all j between 1 and n. So my integral now becomes, so taking this summation outside, we get this summation okay, yeah. Now dividing, we divided this c2 at d into n, divided as, say this as t0, t1 subintervals, t2, and this is tn, that is t case. So again, writing the c2d, that is integration c2d, is equal to summation integral tk minus 1 to tk, where k runs from 1 to n. We get this is k is equal to 1 to n, integration tk minus 1 to tk, and this as it is, that is integral summation k is equal to 1 to n f of xj dash comma t into xj minus 1 into dt. Now taking this to summation outside, we get it is double summation, that is summation k is equal to 1 to n and summation j is equal to 1 to n, and summation tk minus 1 to tk, integration tk minus 1 to tk f of xj dash comma t f of xj dash comma t into xj minus 1 into dt, which is equal to now it is summation, again k is equal to 1 to n, and summation j is equal to 1 to n. Now applying my first mean value theorem for this integral, we get it is f of x j dash comma t k j dash xj minus 1 into tk minus 1. So we are applying one second, we are applying mean value theorem for this integral, that is for some tkj dash belongs to tk minus 1 tk for all k between 1 and n, and this is true for all k between 1 and n. Now this yes, so now we shall consider another case that we have seen integral c to d, integral a to b. Next we shall see integral a to b and integral c to d. Now consider integral a to b into integral c to d x comma t dt into d. We shall observe the same in the similar way, that is integral a to b. Now integral c2 is divided as tk's, smaller intervals that we are writing in terms of summation, that is inside the flower bracket, that we write in summation integral. Now c to d is written as summation tk minus 1 to integration tk minus 1 to tk, where from 1 to n f of x comma t dt dx. Now applying mean value theorem for this, we get it is integration a to b, flower bracket, so it is summation a is equal to 1 to n and to n, so it is f of, now with respect to t, so we shall take it as x comma, so the point we shall take it as, so there exists some point, we shall take it as tk double dash because we have already used tk dash, so it is tk, so yeah, tk minus 1 into dx, where for some tk double dash in the tk minus 1 tk, for all, this is true for all k. Okay, now again for applying rewriting this integral a to b as in terms of summation, that is summation integration j is 1 to n, this is integration a to b, now into, that is summation k is equal to 1 to n x comma tk double dash into tk minus 1 into dx. Now again rearranging, we get it is double summation j is equal to 1 to n k is equal to 1 to n integration xj minus 1 xj minus 1 to xj f of x comma tk double dash into tk minus 1 into dx. Yes. Now applying the mean value theorem for this, again that is summation j is equal to 1 to n, summation k is equal to 1 to n, we have it is f of, now there exists some point between xj minus 1 and xj, that is we shall take it as xjk double dash comma, now it is tk, that is into tk minus 1 xj minus 1. Now using again value theorem, for some xjk belongs to xj minus 1 j, and this is true for all j. Using this as well as this relation, using this relation. Now consider their difference, absolute difference. That's modulus of integration c to d integration a to b f of x comma t dx into dt minus integration a to b integration c to d f of x comma t dt into dx. This equal to, now just substituting, so it is summation j is equal to 1 to n, summation k is equal to 1 to n. It is f of xj dash comma tkj dash into xj dash. Now taking the, that is in the both the term these are common, and this is a common summation, so we are taking this common summation, so minus f of xj k double dash comma t double dash, so this is multiplied by that is tk minus 1 and xj minus 1 Now using the properties of other modulus and summation, so it is less than or equal to, so it is summation j is equal to n, summation k is equal to n modulus of f of xj comma tkj dash minus f of xjk double dash comma tk double dash into now this is, since tk is always greater than or equal to tk minus 1 and xj is always greater than or equal to xj minus 1, this is, we are writing the modulus is nothing but as it is, so it is tk minus 1 and xj minus 1. Now if you observe this xj, I think it is xj dash, this xj dash and this xjk double dash both are belongs to xj minus 1 and xj. Also this implies modulus of xj dash minus xjk double dash is difference is less than or equal to modulus of x minus xj minus 1. Now this difference is nothing but it is less than delta. It's less than blah, blah, because we have chosen xj's and tk's such that xj is nothing but we have chosen xj's such that xj is nothing but xj is equal to a plus b minus a divided by n into j, and similar, so therefore this difference is less than delta. Similarly this tkj's and tk double dash, that is also this tkj dash comma this tk double dash, both are belongs to comma tk minus 1 comma tk, this is xj, correct. This now this implies modulus of tkj double dash minus tk double dash. This difference is less than or equal to modulus of tk minus 1 and that is less than delta. That is, these 2 points have distance less than delta, these 2 points have distance less than delta. Therefore using the star, that is whenever x comma x dash less than delta and t comma t dash less than delta, we have f of x comma t minus f of x dash comma t dash is less than epsilon. So using this wait a second, we have this difference is than epsilon. This difference is less than epsilon. That is yeah, sorry, this is less than uh, epsilon. Summation g is equal to 1 to n, summation equal to 1 to n into another is modulus. Yeah, we can write this like this also, no problem. So it is again dk minus dk minus 1 into xj minus 1 x minus 1. So now, yeah, wait a second again. So some problem. Yes. Now this is equal to epsilon into now summation, taking summation, we get it is epsilon into b minus e into c minus d. Now since epsilon greater than 0 is arbitrary, we get this difference is less than epsilon. Therefore this implies we can interchange the integrals. We can interchange the integrals, hence the theorem. Thank you.